Good morning, sir. Myself V. Balaji. I am from Triple department. Now I am going to explain about Poisson's and Laplace equation in magnetostatics. The question is derive the vector Poisson's and Laplace equation for the magnetic fields starting from amperes. Introduction to magnetic fields. Magnetic fields are fundamental in electromagnetism and play a crucial role in various physical phenomena. Understanding these fields requires a solid grasp of Maxwell's equation, particularly Ampere's law. This presentation will be derived the vectors, Poisson's and Laplace equation for magnetic field. Ampere's law overview, and this is the Ampere's law overview, sir. Field inside load long conductor. Here we can observe formulas for this, sir. Ampere's law relates the magnetic field around a closed loop to the electric current passing through the loop. The law can be expressed mathematically as like this represented here, sir. Applying the curl operator. The curl operator provides information about the rotation of a vector field. By applying the curl operator to the both sides of Ampere law, we can explore the behavior of the magnetic field. And here the curl matrix was given, sir. And vector identify for curl. And these are the formulas and representations of curls. Deriving Poisson's equation. The equation can be rearranged to form Poisson's equation for the magnetic field. Poisson's equation reveals how the magnetic field is influenced by the currents and changing electric fields. Conditions for Laplace equation. Laplace equation is derived under the condition of static fields where currents or electric fields do not change with the time. In this case, the terms involving time derivatives vanish, leading to a simplified form. Physical interpretation of Poisson's equation. Poisson's equation expresses the relationship between the distribution of current and the resulting magnetic fields. It emphasizes that the variation in the magnetic field is directly related to the current density in a given region. This relationship is crucial in applications such as electromagnetic design and analysis. And the same is true if the charge distribution was like a surface charge density, a line charge density, a discrete distribution of point charges, a combination of the above. Applications of the derived equations. Applications of derived equations. The derived equations are fundamental in designing magnetic devices such as transformers and inductors. They are also play a significant role in understanding electromagnetic wave propagation and field interaction. Engineers and physicists utilize these equations to solve complex problems in electromagnetism. Summary and conclusion. This presentation derived the vector Poisson's and Laplace equation for magnetic field starting from Ampere's law. We explored the implications and applications of these equations in electromagnetism. A thorough understanding of these concepts is vital for advancements in both theoretical and applied physics. Here we can observe Laplace and Poisson's equations were there. To derive Laplace equation and Poisson equations, we start Gauss law in the point form like delta dot d bar equals to delta dot E bar equals to rho v, and hence the Poisson equations is like that. Is called Poisson's equations applies to a homogeneous media. And this is a clear explanation about Poisson's equation and Laplace equation. Thank you very much, sir.